Okay, it's a very nice pleasure to introduce Raghav. He's our colloquium style speaker today. He would be introducing new areas of this HEPLAT that allows us to tackle many fundamental problems in quantum field theory that are relevant for particle phenomenology and also understanding quantum field theory more deeply. And he will be also talking about new methods like tensor networks that are used in related purposes. So he's from Perimeter, and he's doing his first postdoc, but he has already worked on variety of problems, and he's also starting his new area of research in tensor networks. So we would be happy to learn from him about these new areas of research. Okay, over to you, Raghav.
Okay, thank you so much, Ayan, for the introduction and for inviting me to talk at this IIT Madras Colloquium. Uh, so today I'll talk about some old and new methods for new and old problems. I'll discuss what I mean by the title and discuss the work I've been doing over the past couple of years. Okay, so let me just briefly mention my collaborators. So I did my PhD at Syracuse University, and these are my collaborators. All of them are faculty at respective institutions, except the last one, Judah, who is now a postdoc at Fermilab. So uh, let me just give a brief outline of my talk today. Uh, when I say old for new, what I mean is I'll introduce holography for matrix quantum mechanics and generic Yang-Mills, supersymmetric Yang-Mills theories. And I'll talk about Adscft conjecture, which was uh, around 1998. And then I'll use Lattice, which was introduced by Kenneth Wilson in around 1974, to study this strongly coupled Yang-Mills theory with supersymmetry and see how it can be applied to understand about holography, dynamical supersymmetry breaking, and many other phenomena. When I say new for old, what I mean is I'll introduce new methods, which are tensor network methods, which were developed around early 2000 and 2010 in that decade. And I'll explain how this is a very efficient method to understand some old problems in physics, such as Ising model, O2 models in 2 dimensions and 3 dimension, or for that example, some classic lattice gauge theories such as U1 lattice gauge theory and SU2 gauge theories in lower dimensions. So that will be the two parts of my talk. Okay, so let's just move to the first part. So what exactly is holography? Holography is a basic idea that a quantum gravitational theory in one higher dimension is related to some quantum field theory without gravity in one lower dimension, which is on its boundary. So even though there is no definite proof of this holographic conjecture, it is widely believed and accepted that any theory of quantum gravity will admit a holographic description. The first hints for holography came in the 1970s when Stephen Hawking and Jacob Bekenstein found out the black hole entropy actually was proportional to the area of the event horizon. So, for example, this is the famous formula which we know, which is the black hole entropy in terms of four fundamental constants. So that is why I mentioned four circles, and then the intersection is exactly the black hole formula. So those circles represent statistical mechanics, relativity, gravitation, and quantum mechanics through those fundamental four constants. And this is one of the most celebrated formulas in physics. So this was basically the first hint of holography. Okay, in a parallel particle theory domain, there was another development in the 70s, which was supersymmetry. Supersymmetry is a natural extension of the standard model. It is elegant theoretically and allows us to do several computation which would not have been possible otherwise. It is beautiful in its mathematical rigor, but it is certainly broken in our class in the world we live in, and it has not been experimentally observed until now. So on the left, we see that standard model of particle physics involves quarks, lepton, and the force carriers and the Higgs boson. On the right side, we have the hypothetical world of SUSY particles, and none of them have been seen at the LHC yet. Now, if we combine these two ingredients together, we get the first concrete example of holography, which was given by Maldacena and is known as Adscft correspondence. So this is a well-known correspondence between a five-dimensional quantum theory of gravity in anti-de Sitter space-time and four-dimensional supersymmetric gauge theory on the boundary, which is known as n equal to 4 superangles, as I'll later describe. In the limit of large number of colors, which is the gauge rank of the gauge group, and in the limit of strong Thooft coupling, the quantum gravity theory is relatively simple. It's like Einstein like gravity in the bulk, which is low energy of the string theory, or we say that it is supergravity. So for example, we see that there's a five-dimensional space time here, and there's a very special quantum field theory which lives on the boundary. So this was the first concrete example of two systems which are related to each other by this duality or correspondence. But even though ADS 5 and CFT4 are probably the widely known pair which forms this holograph, are part of this holographic conjecture, there's nothing special about the four or five dimensions as per se. In fact, just within 1 year of that original paper, this was extended to other maximally supersymmetric gauge theories in D less than 4, even though they are not conformal. So so if you look at say lower dimensional superangles theory, they have a running coupling, and it's not dimensionless as in 4 dimension, and they're not conformal. But that is not a hindrance in describing them holographically, in the sense that we can still understand holography using those theories, as I'll later discuss in some detail. One of the other most studied cases, except apart from the one I mentioned, is the ADS3 CFT2 pair, in which a lot of calculations have been done, and probably we understand that case very well. So what exactly is this extension beyond the usual ADS5 CFT4? It says that the maximally supersymmetric Yang Mills in P plus 1 dimensions has holographic interpretation at low temperatures in a special limit, which is actually the decoupling limit, which is just large N and strong coupling, in the sense that the supergravity solution corresponding to these are black P brane solutions. So that was in this paper by Zaki and Maldacena, and that is what we are going to focus on. So even though we'll start from the four-dimensional quantum field theory, which is n equal to 4, we'll go to lower dimensions and understand holography in those dimensions. So to study this interacting quantum field theory in 4 dimensions, which is n equal to 4, at strong coupling, we don't have a lot of tools. There are some tools like integrability and other available for n equal to 4, but if we go to finite temperatures where the SUSY is broken, or we go to lower dimensions, such tools are not available. So we kind of want to understand these general field theories in the strong coupling limit in a basic sense in different dimensions. So one of the things we learned from Wilson is that we should use lattice methods to study the strong coupling behavior. So how about we study supersymmetry on the lattice to understand more about the strong coupling features? So that is the idea behind this program of studying SUSY on the lattice. But as soon as I want to study SUSY on the lattice, it is beset with difficulties right from the start because of the problem related to the supersymmetric algebra. So supersymmetric algebra is just an extension of Poincare algebra, which includes supercharges Q and Q bar. I'm missing a Q bar here, but still. So they are the extension of Poincare algebra, and they have this anti-commutation that the Q and Q bar anti-commutation is related to the momentum, and P, this momentum generates infinitesimal translation, which is broken on the lattice, because lattice only supports finite translation. There are no infinitesimal translation. So SUSY algebra is not satisfied at the classical level. So this is a problem because you cannot hope to study supersymmetry on the lattice if this is already broken. So what is the solution? This took a long time to come, and it took several decades from several groups. And one of the best solutions we know today is that we should seek to preserve a subset of this algebra, and then hope that the supersymmetry is restored as the continuum limit is taken. This is similar in spirit to what happens in lattice QCD. In lattice QCD, we keep the gauge invariance intact on the lattice, but we break the Poincare invariance or the Lorentz invariance. It is not exact on the lattice. But as I take the continuum limit, the point group structure of the lattice and other things ensure that that is restored. So we have a Lorentz invariant theory in the continuum. So what if supersymmetry also emerges something like that if we just keep some subset of that algebra? So this idea has led to an improved understanding and has been used for the results which I'll mention in this talk later on. This is the review which has been used by the community, and it has all the different ways in which we can study the supersymmetric theory on the lattice. This has mostly been because of the work by these people mentioned here, uh, and there are different approaches, and they are just known as orbifolding and topological twist approach. I will concentrate on this topological twist approach, but it is known that both of these are equivalent. So what one can do, the other can also do. The both of them either works or they don't. Okay, so let me just mention what all I can study on the lattice. Not everything can be studied, even with this topological twist method or keeping an exact superchar. So in 2 dimensions, we can study all the supersymmetric theories. In 3 dimension, the n equal to 1, which has 4 supercharges, real supercharges, cannot be studied. While in 4 dimension, n equal to 4 is the only theory which can be studied. I'll later mention that even this is possible because there is some simplification which happens for n equal to 1. So technically speaking, there are only two which cannot be studied. This cannot be studied and this cannot be studied. So as I
Yeah,
can,
how do you decide no? I mean, and
yeah,
what do you
yeah,
mean
that,
by maximal twist?
yeah. Uh, so if I have a supersymmetric field theory, I can twist it. What I mean by twist is I can take the R symmetric group and then make a, so I take the R symmetric group and then I see what dimension I am in. So it has a Euclidean or a Lorentzian rotation group. So what I mean is, for example, by maximal twist, what I mean is, so for example, let's see, if n equal to 4 has SO6 R symmetry group and it has SO4 Euclidean group. So if the Euclidean or the Lorentzian group is a subset of the R symmetry group, I can do this maximal twist, or I can do the orbifolding. But if the R symmetry group is like U1 and the rotation group is SO4, I cannot do that procedure. So that determines what is yes and what is no. So what I mean by yes and what and no is that the R symmetry groups should be sufficiently large compared to the usual rotation group in that number of dimension so that I can pull out a subset of that R symmetry group.
But
Is that clear?
let's take the case of d equal to 4, n equal to 2. There, the
Okay.
R symmetry is SU2. Forget the U1. Let's say
Mm.
SU2, and but SO4 is actually SU2 cross SU2. So we can actually do a twist, and we can get scalar
Yeah, we can do a
supercharges.
twist, but the
But
maximal
what
twist,
goes wrong in the, yeah, it won't be maximal. But what
yeah,
goes wrong with what you, I mean, the way I think of it is that you're looking for some operator constructed from the supercharges, which we'll call
yes,
Q, such that
yes,
Q square is 0. You're not worried about Q bar,
yes,
and you
that's
want
true.
to
Yeah,
realize Q bar supersymmetry explicitly. Is
yes,
that correct?
that's, yeah, that is absolutely correct. Yes.
So I mean, why do you need maximal is my question, really. You don't
Yeah.
need
So
maximal is what I feel.
so I think the reason we need the maximal twist is also related to, so you can do a twist, maybe it's not maximal, but there is a problem which happens when you try to put it on the lattice. So what happens is uh, so suppose you have some lattice on which you're putting this field theory. So the field should map to exactly to that lattice in some sense. So it should be, so if what will happen in that case is that maybe it's possible to twist it, but if it is not maximal twist, then putting those fields on the lattice is going to be problematic.
Okay, thank you.
Yeah. So
And
as I'll
you
show,
have to also discretize. Sorry,
yeah,
you have to also
yeah.
discretize this Euclidean rotation group then when you want to implement this technique
So yeah,
on the
on the lattice,
lattice.
it's, yeah, of course, that is going to happen. But that part is like you try to work on a hypercubic lattice, or as I'll mention, on a special lattice, and then you take the continuum limit and you restore that as in the continuum.
Yeah, okay. So you'd also discretize the
Yeah,
rotation
so
group
yeah,
then,
you
and
work with the, yeah,
and
exactly. So
then.
it's like you work with the latticized version of these things, and then try to take the continuum limit and retrieve the target supersymmetric theory.
So so most of these cases that you described here do not admit spontaneous supersymmetry breaking, right? Like this n is equal to 4 and d is equal to 4 will not admit spontaneous supersymmetry breaking. And
Yes, yes, but as I said, that even this case can be studied in the sense that it cannot be studied using Q exact method, but it has a direct head-on approach by which people in Germany and other groups in Europe have tried to study it. So n equal to 1, for example, can be studied, and there are many interesting features which people have studied in
and
that model.
this is a more phenomenologically relevant or interesting case, right? And if you want to
Exactly,
apply.
yeah, I'll come to that in my talk. Yeah,
Okay.
I'll talk about that. Yeah. Okay, so uh, let's start with this four-dimensional field theory. So I'll present results based on this geometrical construction and the idea of twisting a supersymmetric gauge theory. So basically, naively speaking, by twisting, I just mean that I take spin. So fermions will now transform in this, will become like p forms, integer forms, after topological twisting. So if the fermions are going to become like a p forms after topological twisting, it is easier to put them on the lattice. For example, I can try to put the 0 form on a lattice site, and I can try to put the 1 form on a link, and I can try to put a 2 form on a placket, lattice placket. So this is a natural way in which we can lay out the fields of the supersymmetric gauge theory on the lattice. Uh, to reduce the fine tuning to minimum to get the correct continuum theory, and to identify the twisted fields in a consistent manner, we cannot work with a hypercubic lattice like in people in Lattice Qcd do in 4 dimension. We need a special kind of a lattice, which we call A4 star lattice. So I just show here a 2-dimensional version of A4 star lattice. So A4 star lattice in 2 dimension will be like a triangular lattice, which is A2 star lattice. So you can think of A4 star lattice as a special lattice in 4 dimension, which is just a higher dimensional version of what I show here. That A4 star lattice has S5 point group symmetry, which is higher than what you have for hypercubic, and it has 5 links. So that's a lattice which has 5 links, and those 5 links are very natural to lay out the fields of n equal to 4, because we know that n equal to 4 has 6 scalars, and there are 4 components of the gauge field. So 6 plus 4 is 10. What you do is you have 5 links. So you form a complexified link, and then complexified link, you have a real part and this imaginary part, and those correspond to the 10 components which we need to work with in n equal to 4 dimensions. So all this construction is required in the sense that you want to reduce the fine tuning to minimum. And as we'll see, even after doing all this, it is not very practical for 4 dimensions, as I'll mention.
A stupid question. So on this A4 star lattice, which 5 links you're talking about?
So, so for example, if I look at A2 star, there are there's this one link, then there is this one, and then there's one which goes back. So this is like 3 links I'm talking about. So for example, if I look at square, so let's think about n
But you
equal to
said
2.
5, right? This is what confuses me. Where the
But this is
number
A2
5?
star. For A4 star, it will be 5. I am just showing a lower
Ah,
dimensional
okay. I
version.
see. A lower dimensional version.
Yeah, this is just A2 star.
By A4, you mean the root lattice of A4, right?
Yeah. Yeah, exactly. Okay, so yeah, this is just two dimension, not the exact A4 sheet.
Okay, thanks.
Yeah, one of the important things in this is the basis vectors are not orthogonal. So if the basis vectors are not orthogonal, there's a different interpretation of thermodynamics and other things which we ran into when we were trying to study holography. But yeah, that is one important thing, that you have to do some kind of construction to just because this is not orthogonal. But it's the price you have to pay in order to reduce the amount of fine tuning which you want to do. So as nice as it sounds, it's still not very practical and has been extremely hard to study on the lattice at large n and lambda using the computers which we have available today, even if you go to big machines at Fermilab and so on. There's also a sign problem which is in this n equal to 4 lattice theory, which is more prominent. It is like very strong for strong couplings. There's any additional complications because of being a super conformal field theory with no scales, moduli, and so on, flat directions, and many other things, which I will not go into technical details right now. So
Yeah,
the
but
four
I
dimensional,
actually have a naive question. Sorry.
yeah,
So for QCD, we have a natural scale, like, and then we can say that when we take the continuum limit would be the limit when the lattice spacing is smaller than that spontaneous generator scale. But in n is equal to 4, as you were mentioning, there is no scale. So what exactly the continuum limit should mean is not quite clear, right? I mean, because there
exactly.
is.
So exactly, that's what I mean by the continuum limit is not very well defined. What we have been able to do till now is match to some results from perturbation theory. So you want to match to the perturbation theory results first, and that will give you an idea of how the continuum limit is appearing in this n equal to 4 theory. So that we have been able to do. Not me, but my collaborators have been working on this for a couple of years now. So there's some sense in which you can take continuum theory, but that all but but the whole purpose of lattice is to do strong couplings. So just matching to perturbation theory is not sufficient. So that is why I say that strong coupling is difficult. And also the additional complication which you mentioned, that how to take the continuum limit. At least we understand that for the weak coupling sector, how to take the continuum limit at least.
But at strong lambda, you could also match to holography, right? At high lambda and
Yeah, but
large
the
lambda,
problem is that we cannot go to much strong lambda. So that is the
because of
idea.
the sign problem.
Yeah, well,
What
so,
you
so
some.
the basic idea is you match to perturbation theory close to lambda equal to 0, and then you want to reproduce holography at lambda very strong, but you don't have a very well idea of what happens in between. And that is exactly what I want to study, right? I want to study finite lambda of n equal to 4 to reproduce free energy or entropy or many other things. And that is already infected with
But
this sign problem.
yeah, but what I was asking is that I think your goal is not simply to match with perturbation theory, right? Because
Yes,
that is
absolutely.
something you can do anyway. But if you
Yes.
say that you can only, are you trying to say you can only trust the some of like the perturbation theory results that you get from the lattice, since the continuum is not well defined? Or are you saying that the continuum is somehow well defined in some way that you could actually trust
I'm
the
on,
results from this lattice?
I'm only saying that we can trust the lattice results for very small lambda till what we have done till now, and in that case we have been able to reproduce the results from the perturbation theory, and we know how to take the continuum limit. But we cannot understand those things when we go to strong lambda, lambda greater than 4, I think 4 or 5. So that is the major problem.
Mm-hmm.
We cannot do holography for n equal to 4 at the moment because it seems impossible.
Mm-hmm.
But what I'll
Okay.
describe is I cannot do holography or n equal to 4, but nothing stops me from going to lower dimension. As I already pointed out, the holography is for any p plus 1 dimensional theory. So I can still do 0 plus 1, 1 plus 1, 2 plus 1. And we have done all that in the last 3-4 years. That is what uh, uh,
Okay.
I have been focusing on. So my research over the last few years, and this is what I have been doing exclusively on this front, uh, has been to understand how to do holographic computation, which can be compared to holography in the lower dimensional cases of super-Yang-Mills theory. And in these cases, the sign problem does not seem to play such a big role. There is a natural scale in those theories, so it is nicer in that sense. And we can compare and compare to some interesting finite temperature black hole physics computation. So let me just start with the ultimate simplification, which is going down to one dimension, just 0+1 dimensional quantum mechanics, basically. So we start with n equal to 1, super Yang-Mills in 10 dimensions, and then we try to go down to one dimension. This theory has SUN gauge symmetry and SO9 internal symmetry group corresponding to 9 scalars. This is probably one of the simplest holographic gauge theories with a well-defined gravity dual. This is also known in the literature as BFS's matrix model, and this is given by these 4 people mentioned here. And this is the lattice, basically the action for BFS's model. You have 2 bosonic and 2 fermionic terms. There's a kinetic term for the scalar, there's a commutator term, and there's a fermionic kinetic term and a Yukawa term. So this is a holographic model. There's also another possibility which is known as BMN matrix model. What you do is you start with BFS matrix model. So BFS matrix model is dual to a gravity theory which is on a flat space-time, but then you can add some terms in the action which depends on this mu parameter, and this breaks the SO9 symmetry of the BFSs down to SO6 cross SO3. And what happens is BMN describes some other gravity theory on some other background, which is like a plane wave background. So on a different background, but the supersymmetry is still intact. It still has 16 supercharges. So so we studied BMN matrix model in this paper, and there's an upcoming paper on this. So BMN matrix model is, as I mentioned, deformation of BFSs. So you start with BFSs and add some terms. So you basically add different mass terms for 3 of the scalars, and you add different mass term for 6 of the scalars. So I is running from 1 to 3, and M is running from 4 to 9. And then you have a cubic term in scalars, which is also known as the Myers term in the string theory literature. And then you have a fermionic term. The interesting thing about BMN matrix model is that the flat direction, which are because of the quartic scalar term in the BFSS model, are lifted by giving masses to the SO3 and the SO6 scalars. So that is interesting, because if that happens, it is useful in numerical computations, because flat direction are sometimes problematic because the numerical simulations are unstabilized by those. So in this BMN matrix model case, the lattice computation are much more robust in the sense that we don't have to deal with the divergence corresponding to the flat directions. So for example, this is a work done by Costas, Pennerones, Greenspan, Santos, in which this mapped out the phase diagram of this BMN matrix model. So you have a deconfined phase and you have a confined phase. And at G equal to 0 in perturbation theory, you see that the deconfinement transition happens around 0.076 of T by mu. And as you go to strong values of G, and this is the limit where the gravity is valid, you see that it goes to some 0.106. And everything which is dashed in this figure, at least the dash which connects these two, is unknown. It's not known what happens in between that. This is just a expectation which is shown by dashed lines. So we want to study this model.
So by that you mean like the order of the transition or anything? Nothing is known.
Yeah. So we don't even know.
What is known at the two ends? At least there are some dark lines I see at G near
Yes,
0
exactly.
and G greater, strong G. What is the order?
Exactly. So order is not known. In fact, it is also not known whether it goes like this. It doesn't. It's also not known if something like this happens. So what I'm saying is, if I want to know what is T by mu at a finite G, I don't know the answer. Like somewhere
okay,
here.
Okay.
Yeah, I just know how. I know to 3 loops what happens at this point. I know from holography what happens at this. So if someone gives me G of 10 and asks me where the transition is, I don't know. Not like it's not known to anyone right now. So this is work which we have been doing. So what we are trying to do is, you start at this point and you start with very small g, and then you keep on increasing g. So on the lattice, there is no problem. We can go to finite g's. It works for any g. And even though it becomes hard in this region, we have been able to do some results in this to see how it is interpolating between those two extremes.
And again, a very kind of stupid. What exactly this confined phase is? Could you explain it?
So confined phase has so there's a so I don't know much about the dual gravity side, but the gravity is description is valid only in this point. So this confined phase has no gravity interpretation as far as I know. It is related to this LLM geometries in M theories and so on. Lin five brains geometries, which was in a paper by 2005 paper by Maldacena and other people, just 2 years after the BMN paper. So these these are some geometries which we know on the plane wave, obviously PP wave background. The gravity dual is here, but I think as you go to cross beyond this, this is not known. There are no gravity solutions which are known in this section, and I don't think there are any, or maybe it's very difficult to construct. These
Uh,
these these authors constructed the solution around this region in the deconfined phase.
and then they show there is some problem if you take T by mu. Typically, what you simply look at the specific heat or something like that and show that it becomes.
Yeah,
Some...
I think their method was, I don't know, this paper. So this paper did some computation which I am not familiar with, because it's like numerical gravity computations. But I think their method or the approximations or something happens to their method, and they could only deduce this, and even that computation is very difficult. So
Yeah, but my question was very naive about it. Was just saying that here you have a coupling. The gauge coupling here is actually dimension full, right? So it's
yes,
not like you are generating some new scale by.
this
So
is
what is the order parameter of this confinement deconfinement? That was the
this,
question that I was asking.
so
Is it
this
only in terms of the degrees of freedom that how the so this is what I was not sure. What is the order parameter of the confinement
yes,
deconfinement?
I understand. Also, let me just first mention that this G is dimensionless, and this is defined like this. So now coming back to the question about the order parameter, the order parameter is the Polyakov loop. So you are in a 0+1 dimensional gauge theory. You want to study deconfinement. So you look at the expectation value of the Polyakov loop in the large n limit. So for example, if the Polyakov loop in the large n limit is close to 1, you say that you're in the deconfined phase. If you see that the Polyakov loop is around 0.1, you're in the confined phase. And then you try to see where it goes through the deconfinement transition. So that is what we look into. So the Polyakov loop is the order parameter, strictly in the large n limit. All this is going to happen in the large n limit, but on the lattice, what we try to do is you do with n equal to 5, n equal to 10, n equal to 15, and you try to see the signal getting stronger in that limit, the Polyakov loop, basically. So it becomes completely exact in n equal to infinity limit, the order parameter.
Thanks.
Okay, so I'm not showing any results for this because this is we have so this is already available in this, and then this is work in progress. But this is an interesting model which we have been trying to play around with and see how to make it more efficient, go to larger values of n, study the free energy, specific heat, and several other things. So this is very much in work in progress. So let me go to some of the works which I have finished over the past couple of years, which is 1+1 dimensional supersymmetric Yang mills, which is Maximil supersymmetry. So as I mentioned, we start with this 4-dimensional on an A4 star lattice, and then go to lower dimension in 1+1 on an A2 star lattice. So this is A2 star lattice up here. And we want to study the deconfinement phase transition, because that is the holographic dual of a phase transition between different black hole solution. So for example, when I talk about this 2-dimensional maximally supersymmetric angles, the dual gravity solution can be a black string solution or a localized black hole solution. And there's a famous instability, which is known as Gregory Laflamme instability, which happens for these black strings. So what
Did
happens
we
is,
lose
as
him?
sorry,
Suddenly it's gone quiet. I can't hear you.
hello, hello.
Suresh, there seems to be no problem with audio at my end.
Ah, okay, then it's my problem then. Okay.
Yeah, should I continue?
Yes, please.
Yeah, okay. Thank you. So what we want to study is, we want to look at the deconfinement transition in this supersymmetric gauge theory, and see if we actually see the phase transition happening around this value, which is predicted again by the gravity computations. So different phases have different parametric dependence on coupling, free energy dependence, I would say, of free energy. So free energy in different phases are different. It's a computation between the energy, entropy, and this entropy in this energy in this case, and there's a phase transition. So what happens is, we have a cartoon like this. So everything which we see in this region, in this red, is the gravity phase. On the right side, we have a gravity d1 phase. On the left, we have a gravity d0 phase. And there is this deconfinement transition happening here, which continues to the weak coupling limit. So we try to study that on the lattice. This is the weak coupling limit. We reproduce the results, and then we go to strong coupling, and we see that already that there are huge errors here, because even working with SU16, it is difficult to identify those transitions exactly. But but this is an indication that it seems that if we go to sufficiently large values of n, we should be able to get closer to this red curve. Or for example, if we still are lying below this red curve, then probably it means that there are some corrections to the gravity results. So on the lower panel, I show the Polyakov loop susceptibility with coupling, and we see that on as we go to larger and larger values of n, going from SU6 to SU12, the peak is going to is sharpening at this. So this is the location of the phase transition in the infinite n limit, because the peak is increasing at this point. So this is how we identify these phase transition in general for different cases. uh, since I don't have a lot of time to discuss all the results, I'll just briefly mention 2 plus 1 dimension now, which we recently studied with Toby Wiseman, Simon Cattrall, David, and Joel Geet. uh, so this has a large n interpretation, holographic interpretation at large n and strong coupling. The weak coupling behavior is well known, which is just like which goes like t cube. In 3 dimension, it goes like t cube. But as we go to lower values of t, uh, this has a holographic interpretation in this region, and we see a different dependence on the dimensionless temperature. So T, small t, is the dimensionless temperature, which is just defined like the real temperature divided by 't Hooft coupling, because in 3 dimensions, 't Hooft coupling has dimensions of energy. So that is the dimensionless quantity. And then we try to study and see if we can reproduce this result from our gauge theory computations. So if we can reproduce those results, then holography in this system is correct. And it's a non-trivial check of holography. If we are away from this correction, we have to understand why those differences are there. So this there's a general dependence of the bosonic action or the free energy on this temperature, depending on what the value of P is. So in this case, P is equal to 2, because this is a 2 plus 1 dimensional super Yang-Mills theory. And interesting thing to note is that for P equal to 3, which is n equal to 4, which is the conformal case, the powers coincide. So this non-trivial parametric dependence on power dependence on T, and this T P plus 1 becomes equal when P equal to 3 for the conformal n equal to 4 case. So these are the results which was published in 2020. Here we see the phases of the unitarized Wilson line, which tells us about which phase we are in. So for example, if we go to very high temperatures, it's in a localized phase with no real gravity interpretation. So as we see, as we go to bigger and bigger temperature from T equal to 1 to T equal to 2, it gets localized. And in the limit of infinite temperature, it will be a sharp Dirac delta types distribution. While if we go to the uniform D2 phase, which is the holographic phase at strong coupling and low temperatures, we see that as we increase n from n equal to 4 to n equal to 8, it becomes more and more uniform, with the expectation that in the n equal to infinity limit, it'll just be uh, uh, it will be a distribution like this. So we cannot reproduce that because we are not at n equal to infinity, but we see that the reds is the n equal to 4, blue is the n equal to 8, so it gets more uniform as n is increased. So this is what we call a uniform black hole phase, because the eigenvalues which determine the phase you're in is uniform in this case. Okay, so I mentioned that the different behavior at high temperature and low temperature is something we want to study using lattice computation. So this is the high temperature prediction, which is the orange curve, and the dashed one is the holographic prediction. So as we see, when we are in this region, we are matching to the orange curve. And as we go to the holographic prediction, it becomes very hard because you have to really work with large values of n, which is the SU gauge group. And as you go to small values of t, for example, at here we are at 0.3, you tend away from this orange curve and go to this dashed. So as you take the continuum limit, you go to this. So this is qualitative behavior which we see that agrees to the result which we expect. This is not a precise computation because it's very difficult, and we are the first group probably who has even attempted to do this computation. But it has nice signs that it is going away from the high temperature behavior down to this dashed behavior.
How large n is in these computations?
This is 16 cube lattice on SU8.
And how much time it takes in processor time for the such
These
produce?
results, this is 5 million core hours at Fermilab. So
Oh,
probably 7-8 months of running, probably a year of running or something. Yeah.
my goodness. And
Yeah.
what about the matrix models? When you try to do it, it
Yeah,
takes more
matrix
time,
models are
or?
simpler. Matrix model are simpler, but yeah. So that is why we are now looking at BMN and BFSS matrix models, because those are obviously you can go to SU32, SU40 or
Mhm.
4035 or something like that. Yeah.
I see, I see.
But this is an interesting
Okay.
problem because we are all like, I also want to work on this optimization on large N and other things, and how we can improve this
Mm.
computation. That is obviously a work in progress. Okay, so all this time I was talking about maximal SUSY. What I meant by maximal SUSY, if I didn't get your attention on that, is that in that number of dimension, it has the maximum number of supercharges. Without gravity, it is 16 real supercharges in any number of dimension. When I want to talk about the phenomenological aspects of supersymmetry, it's completely opposite picture, and I go to the minimal supersymmetry. I want minimum number of supersymmetry to start off with and see how the supersymmetric theories behave. So holographic conjectures need maximal supersymmetry, but n equal to 4, for example, cannot accommodate fermions in the fundamental rep of the gauge group. So, for example, we want to look beyond that, and most notably to n equal to 4, n equal to 1 superangles in 4D. And this is most important from Phenos aspects in 4 dimension. Now, we studied this theory before, but not in its full glory. Sorry. Yeah. We first looked at the 2-dimensional version of this theory, which is n equal to 2 comma 2 superangles. So if I start from this n equal to 1 in 4D and go to 2 dimension, I get this theory. So we studied some signs of dynamical supersymmetry breaking in n equal to 2 comma 2, and the results were published in 2018. I'll briefly mention the results in one slide. Uh, so when I want to study, say for example, supersymmetry breaking, I want to one of the things which I can study is the Witten index. So Witten index is sometimes useful, not always, probably sometimes useful to study supersymmetry breaking. For example, if the Witten index is not 0, then SUSY is unbroken, and if it is 0, it may or may not be broken. But the problem is that Monte Carlo simulations which we use cannot compute the Witten index directly, because we can only compute the expectation values. And Witten index is related to the partition function directly in some sense, in some limit. with some special boundary conditions. So it is impossible to study. So what do we do? How do we understand the supersymmetric breaking in this model? So we studied at the vacuum energy in this model. So we go to finite temperature, compute the vacuum energy, and then carefully extrapolate to zero temperature limit. If the vacuum energy is non-zero, SUSY is unbroken. Uh, SUSY is broken. And if the vacuum energy is zero, SUSY is unbroken. So for example, we found that the vacuum energy is consistent with zero, which is SUSY is unbroken for n equal to 2 and n equal to 3. For example, there was a paper in 2006 by Hori and David Tong, which computed Witten index to be zero for the model which we are studying. So when it was computed to be zero, it was not clear whether the supersymmetry was going to break dynamically, because as I mentioned, if it is zero, it may or may not break. So for example, this computation we did was a direct input from the lattice to understand that the supersymmetry is not broken in this theory. This was also investigated separately by a Japanese group by Kanamori, Suzuki, and Andres Webb in WIF in Germany. So they also studied this model and found out similar results to what we had.
Raghav, in the context of this matrix models, there's a claim by Tarek Anu that the BMN1 actually has 4 degenerate ground states. So the Witten index is probably 0, if I remember, but the ground state degeneracy is 4, and it's something that you cannot confirm by lattice methods, for example, whether the degeneracy of.
Yeah, so the thing is that lattice is they are using something like a Hamiltonian method. So lattice is inherently this Lagrangian, and we cannot study the partition function. So it is difficult to do with the methods we have been using, but it is certainly possible if you go to the methods which they have explored using Hamiltonian methods. That is something which we are looking into, but I cannot say much about that at the moment. But yeah, the computation of Witten index is certainly interesting even for matrix models. But yeah, I know the Tarek Anu paper you are talking about, but yeah, I don't know much. I don't know much.
And why do you say you don't have the Hamiltonian method? Because I thought that for a gauge theory, at least you would have the Hamiltonian for the lattice formulation.
What I mean by we don't have the Hamiltonian method is that the lattice is inherently Lagrangian. So you write down the action, then you
okay, in that sense that, okay, you just compute the Euclidean action. Okay.
Yeah, exactly. Euclidean action. So in that sense, I'm saying, obviously there is, if we use some Hamiltonian methods, but classic lattice practitioners are more with the Lagrangian formalism. Okay, so I should go ahead. I think I'm doing very slow on the time. So I don't know. I should probably speed up. So this is n equal to 2 comma 2. So we can study this. So what I mentioned here was for the pure case, in the sense that there's no fundamental matter or anti-fundamental matter. We can think of adding n equal to 2 super Yang-Mills matter to this theory. And this is something which I want to pursue in the next couple of years. This is a big project, so probably you need 2-3 years of investment, and want to have a group to study this model. But I don't have any results, but this is something which I want to do in the future. And this is related to this is more in touch with the pheno aspects, because, for example, you can study the mass spectrum of the multiplets in this theory and see whether the supersymmetry is restored, whether it's broken, and many other phenomena. So I don't have time to go into, but it's possible to study using Wilson or the Ginzburg-Wilson fermions on the lattice. And several groups have done. I don't, okay, yeah, several other groups are trying before us, but we have not done anything on this yet. So just want to mention some other problems we want to study using lattice. We want to look at the Maldacena Wilson loop, which is a generalization of the Wilson loop to supersymmetric gauge theories. So Wilson loop normally we associate with the gauge field, but in this Maldacena Wilson loop, you also have coupling to the scalars, because there are scalars in super Yang-Mills theory, and we want to study that. A big problem for the next decade or so is to understand the coupling dependence of the free energy or the entropy of n equal to 4 at finite temperatures using lattice. But that is that is probably not going to happen very soon. One of the things which my collaborators are studying is to understand the static potential and anomalous dimension of operators in n equal to 4 super Yang-Mills. But I don't have anything to say about that, so I'll just move to the next part of my talk, which is the tensor networks formulation of gauge theories and how it is useful.
Yeah, just before that, can I ask something about your first or the matrix models again? So I
Yeah.
thought that this confined phase has to do with something with fuzzy spheres, right? I mean, so this, which is probably doesn't have a proper geometric description, but it should be fuzzy sphere like. But what I was asking, very nice question. How is it connected to a Polyakov loop? I couldn't get it. I mean, why should the fuzzy sphere have a non-trivial Polyakov loop?
Let's see. So you're you're right when you say there are fuzzy sphere solutions in BMN matrix model, and there's a phase transition. So fuzzy Polyakov loop in the confined phase. Yes, I always thought about this as starting from the deconfined phase, where it is close to one, which corresponds to the center symmetric uh, broken phase in the gauge theory side, where it is close to one. And then as you go through this, you go through a transition to. So, yeah, I don't know the interpretation, but it seems like if the picture is going to hold, then. Oh, yeah, okay, I see. Okay. Yeah, so the thing is that, yeah, okay, let me see. The the non-vanishing values of Polyakov loop corresponds to some sort of presence of some sort of a horizon in the black hole picture. So for example, it is related to whether that cycle is non-contractible or contractible. So for example, if I see a Polyakov loop value which is very close to one, I say
But the
that there's
Polyakov loop is simply the time loop, right? Ah, because but you're saying if the horizon has a structure, then
yeah,
it will
exactly,
it will not contract to zero. It will go to some.
exactly, exactly,
Okay.
exactly. So that is
I
why
see.
that when it is in that phase, there's a proper horizon structure. When you go to the confined phase, you lose that structure, and probably you also lose the entire geometry, and that is why the fuzzy spheres don't have this geometry. I think that is the picture. Yeah,
Okay. Thanks. Okay.
yeah,
Thank
no problem. Yeah. Okay, so let me just go to the second part of my talk, which is tensor network. So tensor networks inspiration come from another work which was pioneered by Kenneth Wilson. So Kadanoff and Wilson in the 1960s and the 70s were trying to understand the renormalization group for condensed matter and spin systems, and they came up with spin blocking and numerical RG, which was later extended to DMRG by Stephen White in 1992. So DMRG is approach which works well for one-dimensional systems, but it is mostly restricted but it is not only restricted to impurity problems like the Kondu problem, which Wilson studied using numerical RG. So DMRG has more greater extension in solving one-dimensional statistical systems. This was later extended by Levin and Nave in 2007 PRL, and that is where the tensor renormalization group came. It is more efficient than the DMRG method and also breaks down at criticality. So if I am sitting at a second order critical point, this method will not work very well because the correlation length increases and this approximation fails. For critical systems, Vidal and Evemly introduced this TNR, and TNR is probably very close to MERA, which I'll talk about later in the next slide. And these work for very nicely for critical systems because if you want to describe a conformal field theory, you want to sit at the critical point of a statistical system, and then you have the interpretation in terms of a conformal field theory. So if you are at around that point, then TNR probably works the best. So these are the different tensor network methods. Now, what are the motivation which led me to study, led me into tensor networks? One of the prime motivation is that there are a lot of interesting systems where Monte Carlo method, lattice methods fail because of the sign problem. And another important thing is that the partition function, or directly the what we call Z, is inaccessible using the Monte Carlo methods. So we want to use tensors. Tensors also provides an arena for studying lower dimensional critical and gapped systems, and much more efficiently than any other numerical method which is available today. And tensor networks have recently also played an important role in understanding ADS-CFT to some extent, because what happens is you start with a quantum state at the boundary, which describes, for example, a critical spin chain, and then you go in the RG flow, and the RG flow is the direction extra dimension in the holographic dictionary. So there are a lot of motivation to study tensor networks. So what is the
Raghav, can I
basic?
ask a question, general question?
Yeah, sure, Suresh.
Okay, all the tensor network stuff I have seen involves spin systems only. And can these things be extended to fermions, proper fermions? Because
Yes, so
sign
that is
problem, how would you handle the sign problem?
so this work has picked up in the last 4 5 years. So basically what I mean by sign problem is that the Monte Carlo is based on a statistical method, right? You do importance sampling, you recognize that the e to the minus s is like a Boltzmann weight. It cannot it has to be the action has to be real and so on. The tensor network method is a deterministic method, not a stochastic method. So you don't do any sort of a sampling in tensor network method. You write down the partition function, do some sort of approximation and truncation, and then flow it under coarse graining. And then if you do the flow sufficiently many times, you go into the thermodynamic limit.
Yeah, and my problem is with the truncation. I mean, the thing is
Yeah.
that suppose you have a, fermion, this thing, it matters the order in which you write the states. I
Yes.
mean, you'll have a representative for one class, right? I mean, if you exchange
Yes.
fermions, you get a sign. But
Yes.
now when you do this thinning, how do you do it? I mean,
Yeah, so I have not worked on fermionic tensor networks till now, but I'm
mhm.
planning to start working on them. But there are methods which are called Grassmannian TRG. So Grassmannian TRG methods have been developed by these Japanese people, and they have studied, for example, simple models like Turing model and other things. They have
Okay.
studied using that. So Turing model, for example, has been studied using.
Mhm.
So obviously fermions has been handled and has been seen that
But
you
those
can.
are 1 plus 1 dimensional models.
Yes, yes, yes. Most of
Oh,
these are 1 plus 1 dimensional.
yeah. No, the thing is that in 1 plus 1 we have bosonization, etc. We can do
Yeah,
things.
that's true.
We
That's
can,
true.
and so
Yeah.
so really
Yeah.
starting from 2 plus 1 is onwards
Yeah.
is
So
where my question is.
what you are asking, I would say, is at least some years away. So first, you
Okay.
want to study uh, non-fermionic systems in higher dimension. That is what we are doing right now. And once you get a handle of that, you go to the fermionic system in those dimensions. Yeah, but I
Yeah,
Excellent.
but I
understand.
think there are some new methods where the fermionic systems are being used using tensor methods. There's a very lot of new papers on it. So what they do, they rewrite wavelet transforms, a quantum version of it in tensor network language,
I
and
see.
then they are able to write fermionic ground states or non-trivial fermionic states with arbitrary correlation
Yeah.
functions.
How do you do the
So
thinning? That's
essentially,
where I mean, see in tensor networks, etc. This thinning is done in two-step process, right? Then you do this unitary transformation, etc. This is where
Mhm.
the problem will come
uh-huh.
in. How do you do the thinning of the Hilbert space?
So they
Uh,
don't have any such. So they have this multi-scale stuff already built in this. In this. So basically, they have like 2 x 2 unitary, some hierarchical network of that or certain
Mhm.
depth, and
Mhm.
then they compose this kind of networks together to build higher class. I can show you.
Yeah,
So
yeah.
it's a very
But
brilliant
there for, I
construction.
mean, for spin, I understand how to do all these things, at least
mhm.
conceptually. I mean,
No,
I
no,
don't know.
even
I have
for
never done.
fermions, this works. For fermions,
Okay, yeah,
this way of putting
maybe
it
I and we
works.
should discuss
Yeah, we
offline, and you
can.
can give me the
We should
references.
Yeah,
discuss it later. Yeah, yeah.
Yeah,
there are a
okay.
lot of recent
Go ahead,
developments. Yeah.
Raghav.
Yeah, okay,
Mm.
sure. So let me just go. So basic idea is just like the Hilbert space is. I have to go a little quickly, but the basic idea is that you want to reduce the number of degrees of freedom by doing some sort of truncation, as Shudesh mentioned. And the problem is like how you do that efficiently, so that you reproduce the ground state, low energy dynamics of say some system with local Hamiltonian and so on. So that is the basic idea. So how do you understand how do you identify those relevant state? One of the things which we have learned over the past decade or so is to look at the entanglement entropy. So for example, the entanglement entropy for the ground states corresponding to local Hamiltonian scales in a particular way, which is known as area law states. So you have a big Hilbert space which is 2 to the n, but then you go to area law state which is order n. So you only focus on those states which are related to that red blob you see, and using those you can make efficient tensor network description like matrix product states and so on, which people have done. Okay, so let me just mention two important networks here, which is tree tensor network on the left, which is very good for gapped system which have finite correlation length, satisfies area law. And then on the right you have mera, which is a efficient description for a critical system. In addition to the isometries which you see on the left as well, you have disentanglers, which is a unitary transformation which reduces the amount of correlation and reproduces the correct fixed point behavior. Okay, so this is another Mera slide which I have here. The basic idea which I want to show is that uh, Mera is very closely related to the tessellation of the hyperbolic space. And this idea was proposed by Swingle in 2009. What I mean by that is, if I take some spin chain like this, and pick up a length L like this, and I try to compute the entanglement entropy corresponding to that L. So I take a cut like this. So this cut will go like log L. So for example, if this is L, this cut will go like log L, and the entanglement entropy will go like log L. This can be easily seen by how many bonds you're cutting. So for example, if I look at two sides, I'm cutting one bond and one bond. So that's why I mentioned 2 comma 2. This is the number of spin sides, this is the bonds you are cutting. And you can see that as you go to bigger and bigger lattice, the number of sides, the growth of number of bonds you're cutting is only going like log L. So this is a log L description. So log L is also what you get from ADS3 computation of entanglement entropy using root, Takanagi, and so on. And this is a very valid area of research where you want to understand what is the Mera capturing. I will skip this slide because just I've already mentioned about that. So what I use in some of the results I show is something called a higher order TRG. This was introduced in this paper. It is good for spin systems and statistical systems in various dimensions. It is not as good as TNR for critical systems, but TNR is very complex numerically, but this method is more uh, approachable. And if you're sitting away from the critical point and you just want to have a qualitative idea of the phase diagram, this method works better. Okay, so let me show you one slide example of what happens when I do this tensor network for 2D easing model squared lattice. The exact solution is obviously known from Onsager's work. This is the free energy, this is the critical temperature, and I want to do tensor network computation and reproduce these results. So this is what you see on the left plot. H equal to 0 TRG results are the ones which you see in red, and on the hollow black circles, and the red is the Onsager result. There's a perfect agreement. And then you compute the specific heat. You see that the peak of the specific heat is consistent with the expected value of the critical temperature, inverse temperature. So these plots took 100 seconds on a modern laptop. So this is really efficient. The tensor networks probably are the only method today which you can make these plots in like 100 seconds on a laptop. So this is very efficient for 1 and 2 dimensions um, classical statistical system. This is just to show how effective they are. Okay, so what I studied was this classical XY model in this paper. So classical XY model is 1 degree higher than in complexity than the Ising model. So people have looked into it, but using some efficient algorithms, I tried to look at this model and understand the phase structure, because this model is very well known because of the famous Berezinski-Kostelis-Thouless BKT phase transition. So we want to see how much tensor network can help us understand in those, identify the location of those phase transition. So the Hamiltonian is just given by the nearest neighbor simple coupling term, which is J is the exchange coupling. And then I add a magnetic field which breaks the O2 symmetry, global symmetry. And then you do the basic expansion, and then you write down the tensor corresponding to that. So this is the tensor corresponding to the two-dimensional XY model. These are the Bessel function, and the indices are running from minus infinity to infinity. But obviously we cannot do minus infinity to infinity on the computer, so we truncate it. And the truncation determines how much information you lose. And the truncation becomes very crucial when you're close to the critical point. So that is what we explored in this paper. We had some results. And then this model has been studied using Monte Carlo method until 2013. And then from 2013, it was studied using tensor network methods. So our computation gave the most exact result for this, because we use some efficient tensor algorithms, and we reproduce almost the level of precision which was obtained by Monte Carlo after several years of study. So this was an interesting model, and we see that the critical temperature corresponding to the BKT transition is given by this.
Raghav, you study the quantum and then you take the classical
No,
limit in this way?
no. This is classical. This is in 2 dimension. So I have
because in the beginning of the slide you had this comment, that's why I got confused.
Uh,
No, in the slide where you showed the results. Sorry.
I see. Let's see.
Taking h bar goes to okay. The Monte Carlo methods take the h bar goes to 0 limit. That's what you mean.
No. H. It's not h bar. It's the h of here. The magnetic field.
The h here. Sorry.
Yeah. So I start with the XY model. I add a field because I want to add some field and then take to 0 just to identify the behavior, how it responds by computing the susceptibility and so on, just to determine the phase transition. So that is the H we have. And then we take the H to 0 limit and get the phase transition.
And the order parameter is this correlation length, the BKT correlation length.
Yes. Okay, so there's another system we studied in 2019. This should be 2019, not 2018. There's a typo here. But yeah, it's a simple SU2 lattice gauge theory with Wilson action and some matter term. I'll just skip and show the results. So for beta equal to 0, there's a strong coupling expansion, which we do in lattice gauge theories. And you can write down the value of Polyakov loop exactly in terms of Bessel function. And this is just given by this. So this is the exact value. And then we do the tensor computation and see it exactly sits on this. One thing which I should mention here is that when I do SU2 lattice gauge theory, ideally this sum here is the most important thing. This sum here is over all the irreps of SU2 gauge group, right? So when I show results, I only consider, for example, R equal to 0, R equal to half, or R equal to 1. So these are the only reps I consider, because I cannot consider all the reps of SU2 gauge theory. What happens is, if you are at beta equal to 0, this is more than sufficient, because the convergence in R is very quick. When you go to very small, very large values of beta, this becomes a tricky problem, and that is what we are still exploring. But the results are consistent for beta equal to 0, and also up to beta equal to order 10 and kappa equal to 2. Kappa is just the matter coupling, which we write here in terms of the link variables. So we studied this model, and what we looked in is there's a crossover in this model from the Coulomb from the confined phase. So if I had kappa equal to 0, I would be in the confined phase, because it confines for any value of beta. But as I increase the value of kappa, I go from the confined phase to something which we call Higgs phase. And how do we study that? We look at the Polyakov loop correlator. If the potential goes proportional to d, like it is going in this case, we are in the confined phase. If the potential is independent of d, for example, it's proportional to d here, and then it is independent of d this, so that corresponds to the Higgs phase. So these results we obtained using tensor network methods, and this was the first time we studied some gauge theory using truncation over irreps using tensor network methods. So these were nice results, but we have to improve we have to understand more about the truncation and understand more complicated gauge theories like SU3, for example. No one has studied SU3 gauge theory using tensors till date. So that is still a very much open problem. How do you understand, even in 2 dimension, forget about the 3 higher dimension, because tensor network methods are not optimum there till now.
Sorry, but this is for the statistics. This is still a statistical mechanics model. It's not a, you don't have H bar here, right? That's for
Yeah.
confirmation.
So what I mean by this is, yeah, in the sense that I write down a Wilson action and then I compute the gauge theory, in the sense that I have a Wilson action, like a Pluckett term and a link term.
No, I understand. Yeah.
Yeah.
But still, I mean, this is an interesting problem because you're studying this in
The good thing about this is, for
finite
example,
temperature.
yeah, the good thing about this is I can easily add a chemical potential, right? There are a lot of models, lattice models, in which if you add chemical potential, you are just absolutely handicapped, in the sense that Monte Carlo fails. There are very less methods which are available. But tensor networks, we are now looking at some models with, for example, with the chemical potential. So that is still interesting avenues. What happens to SU2 gauge theory with chemical potential, for example, in 2 dimensions, so on. So those are interesting models which we want to study in the future. One of the things which I'm working on right now is some higher network. So I mentioned all the results were for 2-dimensional classical statistical system or 2-dimensional Wilson action and so on. There have been recently some development in 3-dimensional classical statistical system using some nice decomposition in terms of triads, which I show here. So we are exploring this method and trying to study some spin models in 3 dimensions now. So this is a work in progress. I just wanted to bring this. So I'll end by saying, mentioning some open problems, some of which I've already mentioned in the talk. We want to study SU3 gauge theories or the Wilson action using tensor networks and the large N gauge theories in the future. We also want to look into the quantum simulation of spin models and study real-time evolution of, for example, supersymmetric gauge theories with 0+1 dimension, more closer to the Hamiltonian picture as we discussed before, and then move to large N probably, and then develop some higher dimensional tools which can probably shed light on holography as Mera did in 1+1 dimension. But these are all problems for the next 4 or 5 years, uh, which we want to look into. But these are all interesting challenge problems. So yeah, thank you for the opportunity. This is the end of my talk. Yeah.
Yeah. Thanks a lot for this very nice talk. So questions?
Thank you, Raghav.
Suresh?
No, we've been bombarding him enough.
Yeah, I think so. Yeah, we already had too many questions.
Yeah.
Maybe Tanay can ask something.
Tanay.
No, I don't have much.
Okay, so yeah, so because you mentioned this real-time thing, just wanted to ask, especially SU3 in real time could be an interesting problem because there are this plasma phase requires such simulations in real time, this
Yes.
overoccupied. So they put
Yeah.
classical Yang-Mills on the lattice. And do you have something to comment there that you could look into in your method?
People have looked into SU2. The SU2 real time people have started doing over the past couple of years. SU3 is little far still, but I think there's one paper by a group in Italy. I think they use something called a quantum link model to study that SU3 gauge theory. I think that is the only paper I think which is available. But one has to study this quantum link descriptions of gauge theories. I don't have anything more to say about that because I have not looked into that very closely. But yeah, these are I completely agree that SU3 real-time evolution is the real deal in the next 4 or 5 years. If you can study that, it will be a big, very interesting.
Okay, Raghav, thanks for the very nice colloquium. We will be in touch.
Yeah,
and,
pleasure.
Okay, have a very nice day then.
Yeah, thanks, Ian. Thank you
Thanks.
so much.
Bye.
Bye-bye.